Hello, in this video, we will be talking about the uniform distribution. Let's take a look at this example. A discrete probability distribution based on the random variable rolling a regular die. We talked about discrete probability distributions in the previous video, and I gave you this example actually. You list all the possible outcomes, and in this situation, when you roll a die, all possible outcomes will be all numbers from 1 through 6. And in the next column, we associate all of these outcomes with the corresponding probabilities. In other words, I am looking for the probability of rolling a 1 when I roll a regular die. Well, we all know that probability of rolling a 1, it's 1 over 6. Probability of rolling a 2, it's 1 over 6, and so on. All of these probabilities are actually 1 over 6. If you think about this having the same value, make us think of this graph. Each outcome will be represented, each outcome can be represented by a bar or by a vertical line. And since they all are 1 over 6, they will all have the same height. I am looking right here at a very large scale. Here is the graph, and by looking at this graph, you do realize that we are dealing with a uniform distribution. This is the shape of a uniform distribution, and this is the result of graphing a discrete probability distribution. But what if we have a continuous probability distribution? So think of this example. Suppose the distribution of arrival times is uniform with a minimum of 2 minutes and maximum of 15 minutes for fire trucks reaching the scene after being called. So what is the random variable? The random variable in this case will be arrival times, which means the amount of time for some fire trucks to reach the scene after being called. I'll just simply say time. Well, we all know that time is a continuous random variable. And this situation is related to a continuous random variable, which is uniform. So when that happens, we are talking about a uniform probability distribution. And we will learn some definitions related to the uniform probability density function. However, to continue with this example first, we will define A as the starting time, which is 2 minutes in this situation, and B as the ending time, which in this situation will be 15 minutes. And we will use this notation for the random variable. We will say it's uniform and is between 2 and 15 minutes. So on the first place right here, we always put the starting value. Where does it start? And on the second place right here, you put the end value. So the uniform probability density function is defined as U, and this is the notation, in parentheses A, which is the starting of the values, and B, which is the ending point of the values. And the function is defined by this formula, 1 over B minus A, for values between A and B, and 0 for X less than A or X greater than B. The mean of such a distribution is given by this formula, and the standard deviation is given by this formula. In this course, we are not concerned with where these formulas come from, but we will need to use these formulas to solve uniform probability distribution problems. So here is one formula we're interested in because we will always be looking in between A and B. And here is the other formula, and we will need to remember these formulas. And this is the other formula, which is the formula for the standard deviation. F of X plays a special role, and we will see why we need to remember all of these formulas when we solve application. This will be the type of questions we will answer in this video. What is the probability that X is less than some number K? What is the probability that X is greater than some number K? Or what is the probability that X is in between two numbers, K1 and K2? And I can also add the probability that x is some value k. Since we are dealing with a probability distribution, which is uniform, it's a good idea to actually graph the probability distribution. And I will simply use the information from before, the uniform distribution that is about arrival times for fire trucks at some scene. And we have the values of 2 to begin with and 15 minutes to end with. We know this is a uniform distribution. So the graph will look something like this. And I want you to look at this shape and realize that this is actually a rectangle because it's a uniform distribution, right? And make sure you understand that the area under the curve, in this case, this will be the straight line, right? It's 100%. This is at the basis of all we do in terms of finding the probability, because the probability is actually associated with the area under the curve. So a few things that you have to remember is the fact that f of x that we were defining in the previous part is actually the y. Y is f of x. And because we already know how to define it in this situation, I have f of x as 1 over b, which is 15 minus 2. So for our problem, this number right here will be 1 over 13. So we are dealing with this rectangle where you have the side, this side, which in this case is the width, is 1 over 13. And you have this length, which is 13. And we have 100% of the area right here. So in order to answer questions related to what is the probability that x is less than some number, let's just put some number right here, k, and we will drop a vertical line through k. And x less than k means find this area. So we'll simply have to find area of rectangles and, of course, identify the length, the width, multiply those two, because I will simply say as a general case is the base times the height, and of course associated with the shaded region. So first sketch the graph, shade the region, and then you'll simply have to figure out the two dimensions that you have to simply multiply to find all of the information. So all of this will be base times height, but it's corresponding to different shaded regions. So make sure you look at a shaded region corresponding to the specific situation. You'll have to graph it. You'll have to sketch the graph. You'll have to draw it, and then just find the base and the height. Now, there is one extra question. What is the probability that x is k? Think of this. What is the area of a line? A line doesn't have an area because it doesn't have width. So probability of x being one line is just 0. And that's why in this case, if you put the equal sign or not here or there, it really doesn't matter. You can put the equal sign, you can remove the equal sign. The answer will be the same because a line doesn't really have an area. And then we will do some other type of problems related to finding the percentile. And in this case, you'll have to think the other way around. Given the area, you'll have to find the corresponding value. So in order to solve this type of problems, you will have to set up an equation and find the value based on the fact that you know the area. But again, it's based on the area of a rectangle. So let's now see how this all look like on a very specific example. Using the above continuous uniform distribution of arrival times, which is with the minimum of 2 minutes and a maximum of 15 minutes for fire trucks reaching the scene after being called, what is the probability that a fire truck will reach the scene within 7 to 10 minutes? The first thing to do is identify the random variable. And we know the function f of x then is 1 over b minus a, which is 1 over 13. We will sketch the graph. And the graph goes from 2 to 15. And this shape is actually a rectangle. It goes up to this value right here. So it will be 1/13. This is very important, right? And now I'm looking for these two values. And I'll just estimate this as being 7 and this as being 10. The question is, what is the probability that the fire truck will reach the scene within 7 to 10 minutes? 7 to 10, this is the area corresponding to that situation. In order to find the probability, I need to find the area. What is the distance between those two? Well, the distance between 7 and 10, it's 3. So this is a value. This is this side of the small rectangle. And what is this side? Well, this side is actually the same as this or as this, meaning this piece right here is 1/13. So in order to answer the question and I will be using the symbols, I'll be using these two numbers, probability that X is between 7 and 10. It's actually 3 times 1/13, which is approximately 0.231. So make sure you use the appropriate notation. This is the notation when you show your work and you state your answer using 3 decimal places. Next question. What is the probability that a fire truck will reach the fire less than 6.5 minutes? What I always tell students to do, sketch the graph one more time. For each problem, you sketch a separate graph. Don't try to answer one problem using only one graph, because that will be a lot of work and you may get lost among your drawings. The figure will be too busy. So what I'll do, I'll simply write down, this is 2 to 15. So it's the same thing. We have time. This is the random variable. And I have this 100% of the area between the two values, 2 and 15. And let's make sure we know that this number right here, which is very important, is 1/13. And hopefully by now we know why. And we are looking for less than 6.5. So 6.5, let's just assume it's here somewhere. I split this area in two, and the numbers that are less than 6.5, of course, will be this way. So I will shade this corresponding area. This is the answer to the question. Probability is this area. So let's take a look at this dimension. This will be 4.5. And this dimension, which you already know, it's 1/13. So the answer to my problem, and I'll be using the notation, X less than 6.5 is 4.5. Don't forget, it's 4.5 because it's 6.5 minus 2. This is the beginning. A 2 is not a 0. Do not assume it's a 0, unless it is actually a 0. But in our situation, this one starts at 2. So I'll just multiply this by 1/13, and the answer will be 0.34. We will continue with more questions using the same given information. Next question. What is the mean time that a fire truck will reach the scene? Mean time. I'm thinking of the formula is A plus B divided by 2. So remember what A was? Well, A was the start value and B was the end value. So in order to find this, I'll just simply plug in 2 plus 15 divided by 2, which is 17 divided by 2, which is 8.5. And let's attach the units measure to make sense. This is the mean time. Next question, what is the standard deviation? And if you did not remember the formula, just look through your notes. The formula for this one is an interesting one. We'll just have to apply it. B minus A divided by square root of 12. In our case, we have 15 minus 2 divided by square root of 12. So take the calculator and use it. And if you do so, you will have approximately 3.75 minutes. Let's just take a look at another question. And this question is, find the 30th percentile. This is a little bit different. So let's see. We start by graphing our uniform distribution. And now we will try to understand what this is, the 30th percentile. Well, you do recall that the percentile is a measure of location. And if you think of what this means actually that 30% of the data values will be located below that specific value. So I don't know what that value is, but I know this whole thing is 100%. So it makes sense to kind of estimate this. And I'll just use a K here. And I would say, I think this is what I'm looking for, because about 30% of this whole 100% is located in here. So this area right here is 30%. How can I find K? Well, I will simply write down the definition, the formula actually for the area. Area is 1/13 times K minus 2. I don't know K, but this value will actually be K minus, okay? So area is 0.30 or 30%. So now I will simply write down the area as 1/13 times K minus 2. This is what it is. And that equals 0.30. And now I have an equation that I have to solve. So I will simply multiply both sides by 13. So K minus 2 will actually be 3.9. Adding 2 to both sides, K will be 5.9. So the answer to my problem is the 30th percentile is 5.9. Let's take a look at another example. A uniform distribution of temperature ranges from 3 to 8 degrees Celsius. So I'll write down this information. First of all, make sure you know that this is a uniform distribution. It says right here. I identify the starting value as 3 degrees Celsius and the last or ending value as 8 degrees Celsius. Now I'm ready to answer questions. If a temperature is randomly selected, find the probability that it is greater than 5 degrees Celsius. So I'm asked to find the probability that X is greater than 5 degrees Celsius. I know to answer this question, I'll simply have to find some area for a rectangle. Let's just visualize that. We're talking about the uniform distribution. And right here we have temperature. And right here we have the function associated with this one. Now, the function associated with this one, and let's just write it down here, f of x. This is something that you have to remember. This is a formula you'll have to remember. 1 over b minus a. So that will be 1 over 5. This is a very important formula. And we put it right here. This is y or f of x. On the bottom, we have the starting from 3 to 8. And you will simply have to look at this, and hopefully this looks like it's not such a perfect rectangle, but at least you got the idea. And we're looking for a very specific one, greater than 5. So if 5 is here somewhere, where do we shade? Well, you look for greater than 5, so it will be the right area right here. And now you simply have to focus on this area. Okay, what are the dimensions of this rectangle? Well, from 5 to 8, I have a 3, right? 8 minus 5 is 3. And from the bottom to the top, I will identify this as this dimension, right? This is 1 over 5. And that's it. We have the result. So the area will be 3 times 1 over 5, which is 0.60. That's how we answer the first question. Find the probability that it is greater than 5 degrees Celsius. The next question is find the mean. For the mean, we think of the formula. And again, this is a formula you'll have to remember. It's not very complicated, actually. It's the mean between A and B. In this case, it will be 3 plus 8 divided by 2. So it will be 11 divided by 2. It will be 5.5 degrees Celsius. This is the mean. Standard deviation. Well, for the standard deviation, you have to remember, again, the formula is not very complicated. And just plug in 8 minus 3 divided by square root of 12. which is 5 divided by square root of 12. The result will be 1.4 degrees Celsius. The next question. Find the probability of a temperature that is between 4.2 and 6.8 degrees Celsius. I will sketch the graph. We are talking about the temperature as a random variable, which is a continuous random variable. And we had the lower as 3 and the other one as 8. And then right here we had 1/5. Sketch the graph. The original one, this is where we have 100%. And this is a rectangle. And we're looking at the temperature between 4.2, let's just say it's here somewhere, I'll just estimate, and 6.8, which is here somewhere around the middle, right? And this all it's given in degrees Celsius. So I will simply take a look at this smaller rectangle, trying to find the area. Well, I think this is not a difficult task. This is 6.8 minus 4.2, which is 2.6. And this other dimension will be the same as this, which is the same as this, right? Which is 1/5. So let's find the probability that a temperature is between 4.2 and 6.8. It's simply the area in red, the shaded area, which is 2.6 times 1/5. And that equals 0.52. Next question is about finding quartile 1. So let's sketch the graph. Get used to this. You will be sketching a lot of graphs from now on. Again, this is a graph about temperature given in degrees Celsius, and the starting is 3 degrees up to 8 degrees. And we are looking at a height up to 1/5. This is the shape. It's a uniform distribution. So we are looking at this shape. And first, we are trying to identify a quartile. In other words, what do we know about the quartile? Well, you do recall that the quartile is actually dividing the data in such a way that 25% of the data is to the left of it, and 75% will be to the right of it. So this is the location of quartile 1. Now we know the area, and we are looking for this value. This is a different type of problem. It's not like before where we had to find the probability. But keep in mind, we did solve a problem related to a percentile, which is also a measure of location. This quartile is a measure of location. It's actually the 25th percentile. The way we solved the problem was setting up an equation based on what we know. So here is what I will do. I know that the area is 25% or 0.25. So I'll simply rewrite the area. I have this as 1/5, which is this dimension. And I have this piece right here, which I don't know, but I will rewrite it as Q1 minus 3. So I will say 1/5 times Q1 minus 3, which is base times height. This is the area, equals 0.25. This is the equation that I will solve to come up with the result. Multiplying both sides by 5 will give me Q1 minus 3, what's in parentheses, equals to 1.25. Adding 3 to both sides will give me Q1 as 4.25. And this is how we solve the problem. The first quartile is actually 4.25. Let's take a look at the final question. Find the temperatures that separates the middle 60%. Let's try to understand what does that mean. Here we have our graph. Keep in mind the temperatures are the values that are located on the x-axis. Those are given in degrees. We have the lowest value 3, the highest value 8. And then on the y-axis, you have the function describing the situation, which is 1/5. And right here, we have the graph, and this corresponds to a uniform distribution. So this will be a rectangle. So when they say find the temperatures They mean, well, find some temperatures right here, some values on the x-axis, right? Because that's where we have temperature. We don't know the temperatures, but they say, okay, in the middle, you have 60%. Keep in mind, inside this shape, you have 100%. So in order to have 60% in the middle, I will try to mark two temperatures, which I don't know, K1 and K2. And look at that area. The area right there around the middle should be 60%. This is what it's saying. So I have to actually find two numbers, K1 and K2, that border this area. How do I do that? Well, there are different ways of doing that. As long as we realize that this is the middle, that means this is all symmetric. 100% of the area will be split into this 60%, which is in the middle, which leaves 40% to be split into two equal parts. And with that being said, we can use this information to find each temperature K1 and then K2, each one at a time. So let's just focus on the first one. I will shade this area right here, which is the blue one. And I will do what we've done before, trying to find K1. What is this dimension? It will be K1 minus 3, which I put in parentheses. And what is this height? Well, this is 1 over 5. It's right here. Yeah. So I'll set up the equation. The area, the blue area, we know now that is 20%, which means 1 over 5 times K1 minus 3 is 0.20. Multiplying both sides by 5, we get K1 minus 3 to be 1. And then adding 3 to both sides, K1 is 4. So here is how we find the first number. Now the second number right here, we can find it different ways. We can associate this with an area with again equal to 20, but this time it's this area. Or we can associate this with the area from the beginning, from 3 to K2. So whichever works for you, I will associate it with this area of 20%. This time is on this end of the graph. I'm looking at the corresponding dimensions. This dimension between K2 and 8. It's actually 8 minus K2. And this dimension is the same as this, right? This is the height. So it will be 1 over 5. So to answer this question, I'll simply write down area, but keep in mind I'm referring to the green area, equal to 0.2. So 1 over 5 times 8 minus K2 is 0.20. Multiplying both sides by 5, I get 8 minus K2 to be 1. Now, solving for K2, from there, subtracting 8 and then changing the sign, we will get 7 for K2. So between 4 and 7, we have 60% of the data, and that 60% is right in the middle. So this will be the type of problems you will see related to the uniform distribution. With this, we conclude the video.